Why do Six Sigma experts worldwide strive for that magical limit of no more than 3.4 defects per million opportunities? The answer doesn't lie in thick textbooks, but in the natural shape of a mathematical bell curve, the normal distribution. If you understand how this curve breeds and how to translate your processes into a so-called z-value, you can expose the quality of any process in the world with a single number. Welcome to this explainer. Variation is really the invisible enemy of quality, and today we're going to decode exactly how to eliminate it. Okay, let's dive right into this. To keep things clear and reduce the cognitive load, here's our roadmap for today. We're going to cover the origin of quality, variation in customer demands, the mathematical power of z-scores, the ultimate Six Sigma goal, and finally, improving with DMAC. All right, kicking things off with Section 1, the origin of quality. Now, modern quality control isn't just some new corporate trend. It's actually a centuries-old scientific evolution. Just look at the timeline of these three absolute titans. First up, Carl Friedrich Gauss. He gave us the foundational math back in the day, the normal distribution, or the bell curve, which uses standard deviation, or sigma, to express how measurements spread around a target. Then, jump forward to William E. Deming. He gave us the control cycle. He and Walter Schubert developed statistical process control, basically proving that if your process only has natural variation, it's in control. And lastly, Taiichi Ohno gave us the flow. He optimized the legendary Toyota production system, the absolute bedrock of lean, which is all about continuous flow and handling customer demand without waste. So, Gauss gave us the math, Deming gave us the control, and Ohno gave us the flow. Together, they form the DNA of Lean Six Sigma. Moving on to Section 2, variation and customer demands, or as we like to call it, the voice of the customer. Let's translate these concepts directly to the high-end e-commerce logistics of our company, BlueprintRM&co. The customer's desire, the voice of the customer, sets hard boundaries for us. Let's say a design gadget we ship absolutely must weigh exactly 450 grams, including the protective packaging material. That's our target. This gives us a lower specification limit, or LSL, of 400 grams and an upper specification limit, or USL, of 500 grams. The customer dictates this acceptable zone. Anything outside of that 400 to 500 gram window, well, that becomes a defect. Which brings us nicely to Section 3, the power of z-scores, where we actually measure our performance against those strict boundaries. But before we get into z-scores, we absolutely have to talk about standard deviation. This is the core metric of unpredictability. Simply put, it tells you how much each individual value normally deviates from the average. The wider the spread of your data, the higher your standard deviation, which means your process is way less stable. Conversely, if your standard deviation is small, your process is highly predictable and stable. You can see how natural processes spread symmetrically around the target mean, creating that classic visual bell curve. The highest bar right there in the middle is where the vast majority of your outcomes land. And as you move further away from that center, out into the tails of the curve, the frequency of those outcomes drops off. Now, what is a z-value? It's simply the distance between your process mean and the customer specification limit expressed in the number of standard deviations, or sigmas. A higher z-value means your process stays far away from the danger zone. Let's look at scenario A. Our Blueprint RM packing line has a lot of variation, a standard deviation of 25 grams. That bell curve is wide. The distance from our 450 gram target mean to our 500 gram limit is only 2 sigmas, so our z-value is 2. This means a significant portion of the packages falls outside the limits, resulting in damaged products or overweight packages. Now look at scenario B. Here we minimize variation through standard operating procedures. The standard deviation shrinks to just 8.3 grams. Now exactly 6 sigmas fit between the mean and the specification limit. The z-value is 6. The curve is so narrow that errors are virtually impossible, a maximum of 3.4 per million. And that's the true power of the z-value. It is the ultimate universal language within Six Sigma. Whether you are measuring the turnaround time of a return shipment or the weight of a package, by converting everything into a z-value, you can compare apples to oranges and instantly show the executive board how capable your processes truly are. All right, Section 4, the Six Sigma goal. Let's talk about striving for perfection. To measure our goal, we use a metric called DPMO, defects per million opportunities. Let's scale up our Blueprint RM&co gadget packing line to see this in action. Say our customers care about 6 specific packing criteria, things like the right box size, correct label, proper sealing. Those are 6 defect opportunities per single package. If we check 2,000 packages, that means we have 12,000 total opportunities for an error to occur. Now, if we find 75 errors in that batch, we calculate the ratio and multiply by 1 million, which gives us a DPMO of 6,250. So, out of a million opportunities, we'd theoretically make 6,250 mistakes. But let's be real, 6,250 is nowhere near the goal. 3.4 defects per million opportunities, that is the formal target. This right here is the holy grail. It's the absolute threshold of operating at a true Six Sigma level. You're quite literally striving for statistical perfection. And this brilliantly illustrates how interconnected all these metrics are. Look at the numbers. If you have over 125,000 defects per million, your process yield is sitting around 87%, which gives you a process sigma of 2.65. But watch what happens as your DPMO plummets down to that magical 3.4. Your yield skyrockets to 99.99966%, and you officially hit that prestigious process sigma of 6.0. Hitting that incredible target actually requires two distinct things, which we call CP and CPK. CP stands for process capability. This basically asks, is our bell curve narrow enough to even fit inside the customer's technical tolerance? But having a narrow curve isn't the whole story. That's where CPK, process centering, comes in. It asks, is our nice narrow bell curve actually aimed perfectly at the customer's target? The K in CPK comes from the Japanese word karayori, meaning deviation. If your process is super tight but totally off-center, you are still going to produce defects. To reach Six Sigma, both your CP and CPK must equal 2. You need a very narrow spread that is perfectly centered. Section 5. Improving with DMAIC. This is the practical path to zero defects. So how do we actually get there? We use the DMAIC cycle. This is your structured, cyclical path to rooting out the underlying causes of variation. DMAIC stands for define, measure, analyze, improve, and control. Let's walk through these steps briskly. First, define. What is the precise why, the output we want to improve based on the voice of the customer? Second, measure. We have to establish our baseline performance and mathematically prove our data is valid. Third, analyze. This is where we put on our detective hats. Because the output Y is a function of the inputs X plus a margin of error, we have to find those root X causes. We lean entirely on data here. Absolutely no guessing. Fourth, improve. We implement targeted solutions to actually fix those X factors. And finally, control. We sustain that brand new standard with dashboards, KPIs, and operational management so we don't just slip backward. Simply put, we find the X to control the Y. The crucial takeaway here is that variation is everywhere, but it absolutely doesn't have to be unpredictable. By defining your customer limits, deeply understanding your standard deviation, and rigorously applying the DMAIC cycle, you can expose and eliminate the hidden inefficiencies dragging your performance down. So I'll leave you with this provocative thought to chew on. How much variation is hiding in your process right now, just waiting to be measured and eliminated? Thanks for joining me on this explainer for education and entertainment.